Okay, so today we'll study in brief about symmetric encryption and one-time pad. Okay, contents I have taken from this University of Berkeley's presentation and the class notes, right? They have the all they on the website you will also find a book, so you can read both. These are the contents. We'll start with base introduction to cryptography. Then we'll look at concept of symmetric encryption. Then we look at one of the scheme called INDCPA. Then we'll study if time permits one-time pad. Okay, so we'll spend now next 3-4 lectures on at least 4 more lectures on cryptography. Rather more than that, we will also study hashing. Okay, all right. So we have in the last class we have looked at the model wherein we have Alice is trying to communicate with Bob, okay, over insecure channel. When we say insecure, it means that the contents that Alice is sending to Bob can be seen by Eve, okay, or it can be altered by 2D or anybody else. Okay, all right. So this is insecure channel. So we have looked at the, we know about these characters by now, right? Okay. We sometimes we also use Mallory. Okay, and all Eve can do is just simply read the message, while Mallory or Trudy can also alter the message. So now we'll have to look at the threat model, okay, and then create security schemes based on these threat models. Okay, and we have looked at, we know what threat models are. When you build a house, then first you have to create a threat model. What kind of threats can we pose? And then while construction comes, will take care of all those possible threat models, right? Similarly here, in when we are when Eve is communicating with, sorry, when Alice is communicating with Bob, then in the whole communication scheme, we'll have to think of some threat models. Okay, considering that Eve is encrypting the contents, okay, using symmetric encryption. So right now threat model assumes that Eve can only do Eve's job. She can just read the message, okay, that's being sent from Alice to Bob. So Eve can just read this message. But in real world, schemes are often vulnerable to more sophisticated attackers. Okay, so Eve is very simple. She her intent may not be so much malicious, just curious to know what's happening between Alice and Bob. Okay, but in real world, there are some people like Alice, like Eve, who may want to know what's happening around, but there are more number of people who want to do more mischievous things or more malicious things, right? Okay, so threat model has to extend. Threat model cannot assume that there exists only Eve. Okay, okay, all right. So now we have come. So the cryptographers have come out with some threat models. Okay, and based on that, they these threat models will be used to analyze confidentiality. Okay, so now there are two columns here. So now here the Eve, that's the one who is in between Alice and Bob. Can she trick Alice in encrypting the message? Can she trick Alice in encrypting the message? Okay, so there's one column. Okay, now it means that Eve has created a message and want Alice to decrypt it. Okay. Okay, I'm sorry. Uh, so can Eve force Alice to encrypt a message and send it to her? So Eve will send a message, say M, to Alice, and can she force Alice to encrypt this message M and send her back this encrypted message to Eve? Okay. The second one says that can Eve trick Bob into decrypting the message of her choosing? It means that now Eve is encrypting a message, and can she force Bob to decrypt a message? Okay. Based on these two things, we have various models. Okay. So the models are ciphertext only. It means that Eve cannot trick Alice into encrypting the message of her choosing, and Eve cannot trick Bob in decrypting the message of her choosing. Then second one is chosen plain text, where Eve can trick Alice to encrypt the message of her choosing. It means that Eve will create a message and send it to Alice, and Alice will encrypt that message. Okay. And then in this model, Eve cannot force, or Eve cannot trick Bob into decrypting the message which Eve has created. Okay. Alright, and similarly there are two other models. Okay, when if in third model chosen ciphertext, where Eve cannot trick Alice into encrypting message of her choosing, but can trick Bob into decrypting the message. And the last one is where Eve can trick both Alice and Bob in encrypting a message for Alice and decrypting a message for Bob, right? Okay, so now out of these models, we will consider in this class this model. Okay, wherein Eve can trick Alice in encrypting the message which Eve has created. Okay, and this is considered to be one of the powerful models. Okay, all right. So now we will consider that this model, and we'll see that how encryption algorithm should defend against it. That's the aim. Okay, all right. So this is the threat model that we have taken, and then now we'll study these algorithms, cryptographic algorithms. All right, you understood it. So there are see, when we study security and we create security methods. Okay, similarly, so here in this class we are studying encryption. Okay, and we started with symmetric encryption scheme, where Alice and Bob will have same key, and it's, ciphertext is being sent over insecure channel. Now somebody who is in between, like Eve, can do some manipulation. Okay, now here she can read the message ciphertext, but at the same time she has capability of tricking Alice into encrypting the message of her choice. Why Eve wants to do that? Because if she forces Alice to encrypt the message of her choice, she may want to get some information about encryption methodology. Okay, or she wants to guess something out of it. But encryption algorithm should be powerful enough that even if Eve is able to trick the sender, that is Alice, into encrypt the message of her choice and send it back to Eve, yet Eve should not be able to guess, or should not be able to break the cryptographic algorithm. Simple. Okay, any question?
No, sir.
All right, so let's move ahead then, right? So now we are going to study all these topics in the class, if time permits. So we may skip possibly one of the algorithms, or we will just discuss in brief. So we'll start with symmetric encryption, then we'll go to one-time pad, and then we'll look at these topics as well. Okay, symmetric key encryption we have already studied in brief in the last class. Okay, we are here. Okay, we'll study these topics, the topics that are shown here. Now, symmetric encryption scheme that we studied in last class is this scheme is meant for confidentiality only, but not for integrity and authentication. We'll see later how we can also have integrity and authentication along with confidentiality. But symmetric encryption is primarily for encryption. Why doesn't it provide integrity? Suppose when Alice is sending a message to Bob, it can be intercepted by Mallory, and Mallory can change the message altogether from M to M1 and encrypt this using same encryption algorithm and send it to Bob. Now intent here is that whatever message, encrypted message Alice sending to Bob should reach as it is. It means now integrity is not preserved here. There is a person in between who can change the contents of the message. Okay, so all right, so we'll look at some of these aspects little later, but let's continue with okay, this concept of symmetric key where that will provide only confidentiality. Okay, when we say message M, now we always think in terms of WhatsApp message or email message or something, right? But note that everything that we do in computer consists of zeros and ones. See, everything that we manipulate in processor or something that we store in memory, whether it's a hard disk or a RAM or flash drive, okay, or we communicate as a message, everything is zero and ones. Okay, and then we have to interpret these zeros and ones to make sense what it is. Okay, you understand this concept, right? In comp science, everything is converted finally into zeros and ones. Okay, so that's how computers work. Okay, whether it's a file or is an image or is a data, is a voice, everything is zeros and ones, and just combination of zeros and ones that has to be interpreted based on some semantics and syntax, and then we can convert into the original form. Okay, so here the message and whatever be the message, whether it's audio, video, whatever, we are not bothered about it. We are treating in this analysis or in this study only as a bit string, which is sequence of zeros and ones. Okay, all right, so this is what we have studied earlier. We have, here is Alice, she is communicating with Bob. She has a plain text which she wants to send it to Bob, and then she uses a key, and then using this key she uses encryption algorithm, and what she gets here is a ciphertext. Okay, this ciphertext she sends to Bob over insecure channel, which is, for example, internet, and then Bob receives it. Bob knows the key, same key, which has been communicated to Bob somehow. Okay, we'll not bother right now how keys have been communicated over internet. We'll look at the algorithm a little later. And then Bob uses a decryption algorithm to get the plain text. This text should be same as the text which Alice has sent, exactly the same, not a bit change. All right, so this is what we do. Now this algorithm, symmetric algorithm, should have some parts, right? First is key generation. This key which Alice uses has to be generated, and it has to be random, right? It has to be random enough such that anybody in between, say Eve in between, cannot guess it. Okay, so the first part is generate the key. Okay, and we looked at the concept of key space, etc., length of key and all that, right? So we're not bothered about this algorithm, how to generate a key. The second is that now we need to, we have a key available, use that key to encrypt message M. This is message M, which Alice wants to send, and she gets a ciphertext C. Okay, now this ciphertext reaches Bob, and Bob uses a decryption algorithm using the same key on the message that is received, which is ciphertext C, and get the original message M back. Okay, these are the simple steps. Any question? No? Very simple. All right. So what properties it should have? It should be correct. It means that whatever plain text is being, so whatever message is sent here, it will get converted into E of M. Okay, and when it's decrypted, you will get the same message M. Okay, everything should, this message should be same, exactly same, whatever the length of the message. Okay, so this is depicted here. Second is efficiency. Encryption and decryption should be fast enough. It should take days or months, right? It should be, I mean, it should be unnoticeable. It should be very, very fast. So efficient encryption algorithm has to be efficient. Okay, third is confidentiality. It means that somebody in between should not be able to decipher or to find out what is M. M cannot be found out looking at ciphertext. That's it. Okay, all right. Now this is so basically we have to define confidentially more clearly here. Okay, so when we say, in general, we have said the confidentiality means that Eve should not be able to read our message. This is not very precise enough, right? It should not be able to, but what if she is able to read something about it, or she can make out something, you know, even if she can make out from ciphered message that this is a, you know, is a business transaction, or a, you know, or some shares being sold, or it's a you know, normal hello message, or is kind of Eve is trying to send some personal message to Bob, right? If she can make out anything, you know, for example, she can make out whether Eve is trying to say dear Bob or yours Alice or something like that, then that's not confidentiality. Or even if, you know, something like you know, if she can find out the last bit of this message is always 0, last bit of M, okay, where M is a plain text which which Alice wants to send to Bob is 0, even that is enough leak, right? That's also not confidential. So looking at ciphertext, Eve should not be able to find out any information. Okay, all right. Now we need to define it more clearly. Now Eve can do some experimentation, and based on that, we can say that whether the scheme is IND-CPA, which is indistinguishability under chosen plain text attack. Now chosen plain text attack model we have already seen, where Eve can trick Alice in encrypting the message of her choice. So Eve has a message, say ME, and she sends it to Alice, and Alice encrypt this using some key K, this message ME, and sends it back to Eve. If Eve is able to do this, then it comes under chosen place text model, right? Now something indistinguishability under chosen plain text model is called IND-CPA. So you look at this method, and we'll say that the scheme or the crypto algorithm is IND-CPA capable. If Eve is not able to find anything under this model, okay, it's not able to guess anything, okay. So better definition of confidentiality is that the ciphertext should not give attacker any additional information about the plain text. So let's design now an experiment, okay. Now we know that attacker, so attacker, which is Eve, is able to get some information or not, okay. So let's design an experiment to test whether the attacker has learned any additional information, okay. All right. So basically we'll look at these points here, okay. All right, just a minute, okay. Okay, so Alice has encrypted and sent either, okay, the experiment is started this way. The Eve sends message M0 or M1, right? Okay, so to Alice, and Alice has encrypted either M0 or M1, which she has received from Eve. Now looking at the message back, Eve should not be able to find out whether M0 was encrypted or M1 was encrypted, okay. So Eve reads the plain ciphertext and tries to guess which message was sent, okay. So Eve sends M0 and M1, and Alice encrypts either M0 or M1 and send it back to Eve, but Eve is not able to guess correctly which was sent, right? And if the probability of Eve correctly guessing is half, then encryption scheme is confidential. It means that if Eve cannot find out, Alice encrypted M0 and M1, where in M0 and M1, if Alice Eve is creating, it means that she knows what M0 and M1 contains, and the yeah, okay, then and Alice picks up one of them and just encrypts one of them and sends it to Eve. Eve cannot find out which one of the two was encrypted. So in other words, ciphertext gave Eve no additional information about the plain text was sent, okay. All right. So here, even if Eve is able to trick Alice in encrypting a message, Eve can still only guess what message Alice sent with probability half. And this definition is called IND-CPA. All right, okay. So it's here. Pictorially, we can look at in this way. Eve chooses a plain text to send it to Alice and receives the ciphertext. So it's Eve. Note that Eve is in between, and her intent is just to decipher or the read what Alice is sending. So, but she is able to trick Alice in or she tricks Alice in uh, basically encrypting the message and sending it back to her. So Eve sends a message M, Alice receives it, which is Alice's challenger, and she encrypts this message M with a key K and sends it to Eve. And she can repeat, Eve can do this thing, send different messages as many times as she wants, okay. So in this period she can send n number of messages, and Alice will encrypt those messages and send it back using some key, okay. After this, Eve sends two messages, M0 and M1, Okay, all right. And Alice randomly chooses one of them, either M1 or M0, and encrypts that message and send the encryption back to Eve. Now Eve has to guess out of the two messages she has sent to Alice, which one has come back with encrypted form. Okay, all right. Okay, now we can say that if she is able to guess with probability more than 1 by 2, then this encryption scheme fails. Okay, so Eve has to guess which one of the two has come back in encrypted form, and if she is not able to do that, then she loses. Okay, and the probability of guessing has to be more than half, significantly more than half. Okay, other, if she is not able to guess, then she loses, right? Okay, any question?
No, sir.
Okay, now Eve can use any strategy she wants to guess whether M1 was encrypted or M0 was encrypted by Eve and sent back. Okay, so now if you have to prove that this encryption algorithm is insecure, okay, proving is there exists at least one strategy that can win INDCPA game with probability greater than half. Now here we say not exactly 0.5, but it can be significantly higher. It cannot be 0.5 0 0 0 0 0 0 and then at the end 1 or something like that, right? All right. Okay. So basically, you know that half is the probability of winning by random guessing. And if Eve is able to do better than random, much better than random, then cyberattack has leaked information, and Eve is able to learn and use it to gain advantage. Okay. Similarly, we can see insecure proving security. It means that for all strategies, probability of winning INDCP game is at most half. If significantly more than half, then is insecure. Otherwise, the method is secure. Okay. All right. Now there can be, of course, edge cases here, right? And so we see that you know. All right. Then we'll come to that little later. So basically, in this, some information has to be leaked by Alice to Eve, right? The mess, and that is that message size, because all messages cannot be of same size. Okay, so note that in every communication protocol there is a length field, because on a channel there is continuously zeros and ones are being sent, then receiver must know where the message ends. So length of the message is always an important parameter in communication. Similarly, in cryptography, here Alice will leak the message length. Okay, because if we say that message length is fixed as 128 bits, and if it is longer than 128 bits, then this scheme cannot be used. Okay, and if we keep the ciphertext size as 1 GB or message size is 1 gigabyte, then if the message is small, then the scheme is inefficient. So if we don't tell length, then it's impractical. Okay. Now here in this game, INDCPA game, M0 and M1, the two messages which Eve sends to Alice has got to be of same length. Okay, all right. Okay. Second edge case is that any scheme is theoretically vulnerable. So note that in security, when we study security, we assume that everything is vulnerable. But in real world setting, is it vulnerable? If the crypto algorithm takes many years, say hundreds years to break, then it is not a practical thing, right? Then we can say that although it is insecure if the time horizon is thousands of years or hundreds of years, but in real time or real world it is secure. Okay, all right. So this IND CPA game is limited to practical runtime. It means that Alice, Eve can send messages to Alice to encrypt only certain number of times, 100 times, 200 times, or something like that, but not for always, right? It means that Eve is limited to only polynomial time algorithms, not exponential time algorithm. And of course, we also ignore edge cases, like if the probability of Eve to win is little more than 1.5. It's like 1.5 plus 1 by 2 raised power 128. So this is a very, very small number. Then we don't care about it. Okay, all right. All right. If the probability of winning is 1 by 2 plus epsilon, and epsilon is negligible, very, very small, then we just ignore it. All right. Okay. To summarize, okay, an encryption scheme is IND capable, or is IND CPA secure if all polynomial time attackers like Eve can win with probability less than 1 by 2 plus epsilon, where epsilon is negligible. Okay, got the point? So this is a model. So when we are using a crypto algorithm, we'll have to, it has to have IND CPA secure. Can we say that the crypto algorithm is IND CPA secure or not? So that will show the strength of the algorithm. Okay. So another concept we'll study before we'll study very simple encryption scheme, which is called one-time pad. Till this point, any question? Are you able to understand the experiment?
Yes, sir.
Okay, let's move ahead then. XOR function, right? You know this function, exclusive OR. Then both are exclusive, both bits are exclusive OR. There are two inputs, and both, okay, these are two inputs. If both are exclusive, or one is 0 and others 1, the output is 1, otherwise output is 0. If both bits are same, then it's 0. Okay. So what are the useful properties of XOR? So any x, which x could be 0 and 1, when exclusive or odd with 0, it gives the same thing, right? If say 0 is exclusive or with 0, it gives 0, which is same as x. It's a 1 exclusive or with 0, it gives 1, which is same, right? Similarly, same thing is exclusive or x exclusive or with x is 0. Okay, x exclusive or y is equal to y exclusive or x. Okay, and then this property x exclusive or y together, once after this computed, exclusive or with z, same as x exclusive or with x, y exclusive or z. These all properties we know. Now something that's of interest is this one, x exclusive y exclusive or with x gives us y. Okay, so effectively what it says that given this one, x exclusive y, you can retrieve y by computing x exclusive y exclusive or x. So effectively cancelling out x. So this property we'll use in encryption, we'll see. Okay. Okay, and it also follows the algebraic rules, right? All right. Okay, simple. So we are now going to study a very simple encryption scheme called one-time pad. It's also called Vernam's cipher. Okay. So one-time pad, or we call it OTP, not one-time password, but one-time pad, is simple and idealized encryption method. Okay, so what it does, it helps us to understand or illustrate some important concepts, though it's impractical in real world use, right? It's not really practical. Okay, so it works in this way. Okay, historically people try to use it, but they found it's not very practical. Now note that message is always in terms of zeros and ones. Similarly, keys are in terms of zeros and ones. Okay. Now key that Alice chooses is randomly chosen of some length. So this is the key. Okay. Now these bits here are randomly chosen. Okay. Now we will study later on how to generate random numbers. Okay. And the message is of the same length. Now the message is not randomly chosen, but the message which Alice wants to encrypt. Note that key size and the message size is the same. Okay, so this is the message which Alice has, and this is the key. Now Alice has to encrypt M using K, and simplest encryption algorithm is do XOR. Okay, this is what we are doing. Bit by bit XOR we are doing, and what we are getting is the ciphertext here. Okay, now the question I'm asking you is that now you have, or Eve has this ciphertext. Can she find out what is the message M from this one? Until unless she knows everything about key. Can she? She received only C. And she also knows that encryption algorithm is XOR. Because we know that encryption algorithm cannot be kept secret, and she knows that it is bit by bit XOR is an encryption method. All she knows these two things. Can she now come out with original message M? Yeah? Yes or no? Okay, when we say is idealized scheme, obviously answer would be no, right? Okay. So now what this message reaches Bob. Okay. So this message, right? The ciphertext reaches Bob, or encrypted message reaches Bob. Okay, and Bob also knows the key because Eve and Bob have the same key. Now Bob wants to recover message M. What will he do? We'll use this method, right? Exclusive OR method that we have just seen here. See, all he can do is exclusive OR between key that he has received and ciphertext he has received, and we'll get this message M back. It's same as the message that we have used here, right? Got it?
Sir, what does ideal condition mean here?
What is the ideal condition?
Yeah.
What is the ideal condition means what here? I mean, what is the question like?
You said this is considering the ideal encryption.
This is ideal encryption because, okay, I got it. What is the challenge here, right? One-time pad. Why it is impractical? Because first thing is that the key generation will come at that we'll discuss. That we'll discuss. See, first notice one thing: the message size and key size has to be same. This is one. If message is 1 megabyte, then key also has to be 1 megabyte. Okay. All right, so these kind of problems are there, and then every time we have to, and we'll look at. I mean, there is also issues about key. Okay, so the one-time pad first is that randomly generate n bit key when n is the length of your message. Note that message size and the key size is the same. These are of the same size. Okay, all right, and then for one-time pad we generate the new key for every message. Okay, and then we use this encryption method. Okay, so because in this something that we call it one-time pad, okay, so one time is what? That we are using the key only once, and this is the method, and this is the ideal method. All right, okay, so bitwise in order to, okay, so once there is a message M which Alice has generated, we have to use the key which is of the same size, and we'll do this operation, exclusive operation bitwise, and get the encrypted message EKM, right? Okay, and then we'll have to use and which we call it C, and then we'll have to use decryption algorithm using same key and C and get the message back. Okay, all right, this is simple. So correctness is that if we encrypt and then decrypt, we should get the original message back, which is fine. So now from our definition of confidentiality, the ciphertext should not give an attacker any additional information about the plain text. Okay, so recall from our experiment that to test confidentiality from earlier, Alice has encrypted and sent either M0 and M1, and Eve knows either M0 and was sent but doesn't know which. Okay, Eve reads the ciphertext and tries to guess. If the probability that Eve correctly guesses is half, then encryption scheme is less than half, at most half, then encryption is confidential. So now, okay, if K is chosen randomly, so both possibilities are equally possible. Okay, possibility 0, that whether Alice has sent M0 or M1. Okay, so now this key has to be random in order to have this probability half, exactly half. Okay, so that's the challenge. So if has learned no new information, so the scheme is perfectly secure, provided this key is absolutely random. Then both then both the guesses by Eve are equally likely, whether M0 and M1. Okay, why is it now? Some question may come to your mind, right? Why it is one time then? What is so good about one time? We are using the key only once, right? What happens if we use it 2 times? Does it reveal any info? Okay, so now we know that one time, if we use the key one time and key is of same size as message and randomly chosen, the scheme is perfectly secure. That we concluded. You agree? Now you may ask this question, why not use the key 2 times? How does it make any difference? Okay, now it will leak some info, right? Okay, so use the same key twice. So Alice receives 2 messages, M0 and M1, which she encrypts, okay, using key K. Okay, and what she has is K exclusive or M0, and second message is K exclusive or M1, because key is being used twice on different messages. So Eve sees ciphertext, this ciphertext, this is, let's say call it C0 and this is C1 over insecure channel. Now looking at these two, can Eve find out something? Okay, if all she does is that exclusive of the two, then she learns about, M0 exclusive or M1, because K will cancel out. Okay, so she learns about M0, the message M0 exclusive dot with M1 bit by bit, right? This info is available, and this is, so this, it means that this info is leaked, that what she has received is exclusive or of two messages. So this, if you use the same key 2 times, then information is leaked. Similarly, you can see 3-4 times and so on, more and more information is being leaked. Okay, all right. So this is the theory. So result is that one-time pads are not secure if the key is reused. It means that ellipse and bob must use different keys for every message. Now, is it practical for every message keys to be generated and to be sent securely to other end, bob? So this is not practical, right? So key generation itself is a problem. The longer the message is difficult to generate the key, because randomness is not free, it comes with cost. And then key distribution, it has to be sent to other end securely. Okay, and for every message it has to be done. Okay, practical application is that you can communicate keys in advance, but again, you have to have secure channel for that. Okay, or there's additional cost, right? And of course, it's not going to help much, although we'll get perfect security, but note that key can be used only once. So every message will require different key, and it has to be securely communicated to the other end. So a scheme can work, but it's very, very difficult to implement and expensive. It's not practical. Okay, all right. So we have studied two concepts today. Let's go back and quickly revise. Okay, just a minute. Okay, all right. So another 2 minutes, we'll revise and close. We have chosen plain text. As a threat model. Okay, where Eve can trick Alice in creating or encrypting message of her choice. Okay, what we have started to study is symmetric encryption. We have studied one-time pad. Okay, we know that we use only bit strings. Any message, anything that we in comp science is bit string. So here message and the keys are all considered to bit string. And then we use in symmetric key encryption. It has 3 steps: key generation, encryption, and decryption. Keys have got to be the same, and how these are to be communicated is another problem that is to be solved. Okay, in order it to work correctly, both plain text, the plain text or message which L is sending, after decryption it should be the same. Okay, it has to be correct, then it has to be efficient, it shouldn't take too much time, it has to be secure. Then we say that security is, definition of security is very vague that we have considered so far. So we define precise definition of security, that Eve or adversary in between will not be able to make out anything, not even guess whether the last bit of the message is 0 or whether it's a transaction or something, from looking at a ciphertext. Okay, so ciphertext should give no information about the message. Okay, then we have looked at a scheme called INDCPA. Okay, where this is an experiment, and then we see that Eve can trick Alice in sending either M0 and M1. So So Eve sends either M0 and M1 and can trick Alice in encrypting any of these, okay, or encrypting any message that she sends. And all right, so in this game we have seen that Eve sends any number of messages, and then Alice encrypts and sends it back. Then Eve sends two messages, M0 and M1, and then Alice randomly picks up one of them, encrypts and sends it back. Based on this, Eve cannot guess whether M0 was encrypted or M1 was encrypted. If the probability of guessing is significantly more than half, then Eve has won the game, otherwise Eve has lost the game. Okay, so however, there are some edge cases, message length has to be leaked. Okay, and then probability of win can be slightly higher than half, right? So, but but this epsilon has to be negligible. Okay, then we come to one-time pad, and we see that this is ideal encryption scheme using simple mechanism called XOR, but it has a practical limitation that key size has to be same as the message size, and key has to be randomly generated, and key has to be securely communicated to another end. And another practical issue is that key can be used only once, right? So this reason is called one-time pad. Okay, we have seen that if you use the same key two times, then leaks information. So the scheme is then non-secure. Okay, all right. That's all we have studied today. Any question? Please go through this content from PPT and also read the book available online. Okay, all right. No question, then let's stop.